Okay, so that's going. So welcome back, everybody. This is the second lecture of the semester, and today we're going to pick up right where we left off on the first chapter of the textbook, which is all about measurement and significant figures. Before we get back into the lecture, just a few things to say. Did everyone get a copy of the flyer that I just passed out? Okay. So I posted an announcement about this on Canvas. You may have already seen the announcement, but basically I'm going to be holding a series of workshops for introductory physics students. They're going to be held on Friday, and they're going to be online through Zoom. So if you just came in, can you take a copy of this? There you go. So each week on Friday, I'm going to be holding the workshop at my own Zoom link. It's the same Zoom link that I use for office hours. So you can find that on the course website, or just type what's on the flyer into your browser. And what we're going to be doing each week closely tracks with this class. So if you notice, the first week, which is actually tomorrow, our first workshop is tomorrow, is all about problem solving in physics as a general concept. Next week, it's all about units and sig figs. And then after that, we're going to get into kinematics. So this is pretty much what we'll be doing in Physics 44 each week. So I highly recommend attending these if you need some extra help with the class. So any questions about that? Okay, and then the other thing I wanted to say before we get started is about the homework, just to clarify. The homework is going to be turned in as a hard copy. You're going to turn in a physical copy. I'm not going to be putting an online submission form up on Canvas or anything like that for homework. Because we meet in person, it just makes the most sense. So most homework assignments are going to consist of problems from a worksheet that I give you and some problems from the textbook. The worksheet I give you generally doesn't have a lot of space to actually fill out your answer. Just think of the thing I pass out as just a statement of the problem. I suggest just working your whole assignment out on a separate paper, just in one document. So any questions on that?
If we're unable to make it to the class, how would we be able to turn that in?
Okay, yeah, so I can make an exception to that if you can't make it to class for health reasons or otherwise. Just send me an email and we'll work something out. What I'm saying as a general practice, if you're coming to class on a day an assignment is due, you'll just turn in the physical copy. Anything else? All right, so like I said, we're going to pick up right where we left off. And we were talking about significant figures last time. And we have two basic rules that we learned about. One applies to addition and subtraction, and the other applies to multiplication and division. As far as when I make a calculation, how am I supposed to round that off? So next, let's get into what you're supposed to do in a more complex calculation. Let's say there's some mixture of addition, subtraction, and multiplication and division, or if you have other functions like cosine or log, what do you do in those situations? So if you have a mix of different operations, it's pretty simple. Just complete the calculation at each step, use the standard order of operations, and then at each step, just keep track of how many significant figures you have. Okay, just use the rules at each step that we learned about previously until you get to the last step and then round there. So let me show you an example of how this would work. In the first example up here, I have 2.145 plus 2.13 divided by 1.54. Okay? So first, I want to take care of what's on top of that fraction, which gives me 4.275. Now, to get to here, I added two numbers together, didn't I? So do you guys remember what the rule is when two numbers are being added together, for how we round? You round to the smallest number of decimal places. So we have 2 decimal places here, 3 decimal places here. So the smallest number of decimal places is 2. So I'm not going to do that rounding yet. I'm just going to put a little bar above the 7, denoting that's my last significant digit in that number. So I have 4.275 divided by 1.54. So now I'm doing a division. What's the rule for that? When I divide two numbers, how do I round the result? Yeah, I look at the two numbers and I say, which one has the smallest amount of significant figures, and I round to that many, okay? So how many sig figs are in the number on top? Well, actually, it's 3 because I'm cutting it off here, right at the 7. So, and then at the bottom, what do I have? 3. So I'm going to round this to 3 sig figs. So before I actually do that rounding, I get 2.776, but I'm putting a little bar above that 7 to denote that's where I'm going to round it off. So what's my final answer? 2.78, okay? So just follow the rules of rounding at each step in the calculation. That's what I'm trying to get across here. Okay, let's do another example where we have the natural log function. When you deal with these types of functions, where you're like plugging some number into it, like plugging in 4.67 into the natural log function, as we see here, just take the output, the result of that, to have the same number of sig figs as what you put in. So if I put in something with 3 sig figs, I'm getting something out with 3 sig figs, okay? So I have natural log 4.67 plus 1.3. I'm going to round the first thing to 3 sig figs because what I'm putting into it has 3 sig figs, okay? So if you punch this into your calculator, you're going to get 1.54, and then there's a 1 after that. But notice what I'm doing. I'm putting the bar above the 4 because that's where I'm supposed to round, okay? I'm not going to do it yet, but I'm just keeping track of it right there, okay? And then add those two numbers together. I have 1.541 plus 1.3. This is an addition, so what is the rule for that again? When we add numbers, what's the rule? Round. Yeah, so if this is given to 1 decimal place right here. That's the smallest number of decimal places of these two numbers. So we're going to round to 1. So that would just give us 2.8. Okay? So that's how this works. Pretty much any example you can ever see is covered in these two examples. Okay, so that's where we're at. The other thing to mention here is that sometimes you're going to have a formula that you're plugging numbers into. For example, I'm showing here a triangle that has a certain base and a certain height, and we know the formula to calculate the area. It's 1/2 base times height, okay? Now you might just look at this and say, well, there's like a 2 here. And normally, if you just see the number 2, how many sig figs would you say it has? Kind of looks like it just has 1 sig fig, right? That's not how we want to treat it here, though. See that 1/2 in the formula, that's an exact value. We know it exactly, right? It's not something we measured and we're not quite sure about it, or we're sort of fuzzy on what the value is. That 1/2 is exact. So that's not going to affect our sig figs, okay? What is going to affect our sig figs is how many sig figs I'm putting in for B and how many I'm putting in for H. Does that make sense? So if you have certain constants in a formula, they don't count towards your sig figs. Okay? So that's the lesson here. All right, so with that said, I want you guys to try one out. Here is a formula. You're going to learn about this later in the second chapter. But for now, don't worry about what the formula means. Just take the formula, plug these values into it, and then tell me what your answer is after you round to the correct number of sig figs. Okay, so this is really about doing the calculation and rounding to the correct number of sig figs. So try it out at your desk, take a few minutes, and then we'll go through it together. Has anyone not received a flyer yet? So I passed these out right at the beginning. Anybody else? Oh, very good. let's take about another minute and then we'll put it to a vote. Okay, so let's reconvene. Again, if you haven't finished yet, that's okay. Just look at what you've done so far and try to see which one of these possible choices is the most likely answer. So who thinks it's A? We want to round this to basically 3 sig figs like this. Who thinks it's B? Okay, who thinks it's C? Okay, if you said B, you are correct. So we want to round this to 0.59 meters. So again, I just want to go through this real quick on the document cam over here, just so we're all on the same page. So our formula is x equals x0 plus v0 times t plus a half times at squared. Again, don't worry about what this formula means, we're just using it. First of all, x0 is 0, so we can just ignore that for now. The value of v0 that we plug in is 2.50, and the units on that are meters per second. Turns out this thing is a velocity. T is the time, that's 3.75 seconds. And then we add that to a half times a, that's called the acceleration. We'll learn about that next week. But it's minus 1.25 meters per second squared. And then we take that same t from before, that's 3.75 seconds, we square that. So here, let's multiply the first set of numbers here with 2.50 times 3.75. If you punch that into your calculator, that's 9.375. But there's 3 sig figs going into each one of those numbers, right? So I should be mindful of the fact that when I multiply 2 numbers with 3 sig figs, I only keep 3 sig figs. So there's the bar above the 7, okay? All right, do the same thing here, multiply all this out, and what I get is minus 8.789 meters, but again, there's 3 sig figs going into it, and remember, this 1/2 factor is not affecting our sig figs, because it's just part of the formula, okay? And so I'll put a little bar above the 8, because we're keeping 3 sig figs. Okay, now, I'm subtracting 2 numbers, and if you punch this into your calculator, you're going to get 0.586 meters. However, look at the 2 numbers we're putting into that calculation. The first one, we're rounding off to the 2nd decimal place. The second one, we're also rounding off to the 2nd decimal place. So the result should be rounded off to the 2nd decimal place like this. And the answer then would be 0.59 meters. So that's how we know, okay? Any questions on that? We're just sort of following all these rules that we learned about so far. Okay. So with that said, we're pretty much done talking about units, measurement, and sig figs for the time being, although of course we're going to see this stuff in lab a lot in the future. But let's move on to something else. Let's move on to problem solving in physics. So basically for the rest of this lecture, I want to just talk about some basic strategies for problem solving that are going to come up in this class, throughout the rest of the semester, and pretty much any other physics class you take in the future. So let's get into that. So in physics, we say the language of physics is mathematics. Every idea that we learn about in physics is best expressed in terms of some equation. So that means we have to be comfortable with our mathematics. Let me just tell you some of the things you should know as a background going into Physics 44. Definitely algebra. You should have a strong foundation in algebra, trigonometry, and then also solving word problems. The worksheet I gave you for this week for homework is all about solving word problems. In other words, can you just take some statement given in words and translate that into some equations? That's really the point of this. Later on, if you take 45, 46, or 47, there's going to be some calculus involved, but not in this class. We won't really touch on any calculus. All right, so again, the rest of this lecture is all about those problem-solving strategies. And why don't we just launch right into an example? We're going to start really simple and then gradually build up to more complex examples, okay? So this is the first example. Let's say you have a midterm exam. There are 20 questions on it, worth a total of 100 points. We've got true and false questions. Each one of those is worth 3 points. And we've also got multiple choice questions that are worth 11 points each. So how many multiple choice questions are there on the exam, and how many true or false questions are there on the exam? That's the question we want to answer. So let's go through it. So first thing I'm going to do is just state what my unknown quantities are. I can pick any variable I want for my unknown quantities, but it kind of makes sense to say T is the number of true-false questions. And then M is the number of multiple choice questions. Okay, so I have two unknown quantities. How many equations do I need to write down to solve two unknown quantities? Two, yeah. I need as many equations as I have unknowns. So what's one equation I can write down that involves these two variables?
T plus n equals 20.
Yeah, so here, I'm going to say it in words first. Total number of questions is equal to 20. So that means T plus M is equal to 20, correct? Okay, what's another equation I can write down?
3t plus 11m equals 100.
Mm-hmm. And what that's saying in words is the total point value is 100, right? So if we translate that into an equation, well, each true-false question is worth 3 points. So if I take 3 times t, that's all the points for the true-false questions, right? And then my multiple choice questions are worth 11 points each. So if I take 11 times m, that's how many points I have in the multiple choice questions. And if I add all that together, it's 100 points, okay? So I want to know the numerical value of t and m, so what should I do next?
Isolate a variable?
Yeah, just isolate a variable and then substitute it. So we can go any way with this, but let's take the first equation we wrote down. I'm going to label this equation number 1. The second one is equation number 2. Let's take the first equation I wrote down and write it as t equals 20 minus m, and then we can sub into equation 2 that formula, okay? So I have 3 times 20 minus m, subbing that in for t, plus 11m equals 100. Okay, real quick, let's do some mental math. 3 times 20, 60 right there, okay? And then I have minus 3m, distributing that into the parentheses. And then I have plus 11m. That equals 100. So 11 minus 3, what's that? 8. So we have 8m. And then if I want to take this 60 and subtract it from both sides, 100 minus 60, 40. So m must be 40 over 8, which is,
12.5.
it's going to be 5. And then t, remember that's 20 minus m. That's 20 minus 5. What's that? That's 15. So we have 5 multiple choice questions. We have 15 true false questions on this exam. Okay? Straightforward, right? I want you guys to try one out. It's actually very similar. The way you approach this one is really similar. It's kind of a goofy example, but let's go with it. So let's say one day you go to the horse racing tracks, and instead of just trying to count how many humans and horses there are, you just count the total number of heads you see, the total number of legs you see. So between the humans and the horses, you see there are 2,550 heads and 5,200 legs. So based on that, how many humans are there? How many horses are there? Okay? Assume a horse has 4 legs, a human has 2 legs. Assume everyone has 1 head. Okay? So try it out, take a few minutes, and see what you get. By the way, the papers I use to write down the examples, I'll just keep these at the front in case you miss anything. You can see this at the end of class.
Did you get this one? Yeah.
Okay. So I know in some of these problems, it may seem a bit rushed, but I'm just trying to get through the whole lecture today. So let's go through it together at this point. And again, we have 2 unknown quantities. We have the number of humans and the number of horses. I don't want to use the letter H for both of those. That's going to get confusing. So how about we say P is the number of people, and H is the number of horses. So what's one equation we can write down that involves these 2 variables?
4H plus 2P equals 5,200.
So what we're saying there is each person has 2 legs, right? Each horse has 4 legs. So if I take 2 times P, it's the number of legs amongst all the people there. If I take 4 times H, it's the number of legs of all the horses involved. And then that equals the number we were given, which is 5,200, right? Okay, So what's the other equation we can write down?
P plus H equals 2,550.
Yeah. And then and I'm just going to write it in words again. We're assuming each person has one head. Each horse has one head. So no half human, half horses or anything like that. Okay. But anyway, P plus H equals, was it 2,550? Okay. And at this point, it's just like the last problem, right? So we're going to sub one of these variables out. We can choose which one we do. Let's just say P is equal to 2,550 minus H using the second equation. And let's plug that into the first equation, which gives us 2 times 2,550 minus H plus 4H equals 5,200. All right? What's 2 times 2,550? Can someone just crunch that real quick? That's 5,100. And then I have minus 2H here. When I distribute into the parentheses, and then I have plus 4H here. And then I have 5,200 here. So what's 4H minus 2H? That's just going to be 2H, right? And then what's 5,200 minus 5,100? Just 100, right? So H must be 100 over 2, or 50. That's how many horses there are. How many people? Well, the number of people is just 2,550 minus H. So 2,550 minus 50, 2,500, right? Those are what we're looking for right there. Okay? Any questions on that? So again, it's pretty much the same problem, just stated in different words. So I wanted to ask you this one. This one involves percentages, which are going to come up from time to time, particularly in the lab setting. So I just want to make sure we can do a calculation like this. So let's say you mix 25 milliliters of pure ethanol and 15 milliliters of water together in a beaker to make a solution. So what is the percent ethanol by volume of that mixture? So take a minute to try to work this out, and then we can go through it together. You guys remember how a percentage like this is calculated? What do we do to calculate this kind of percentage? Yeah, so you take the amount of ethanol divided by the total amount, and then what? To make it a percentage? Multiply by 100, that makes a fraction like that into a percentage. Okay, so what are we getting for this? Just shout it out if you have it.
37.5.
Not quite.
37.5.
I got 62.5%.
Okay, so yeah, it's gonna be it's gonna be about 60%. Let's go through it. Yeah, so here, let me just write down in words what we're doing. If we want to know the percentage of ethanol by volume, what we're literally doing is we're taking the volume of that ethanol, so just that part of the mixture, divided by the total volume, and then we're multiplying by 100. That's just the definition. So what is the volume of ethanol in this case?
25.
It's 25 milliliters, right? What's the total volume?
40.
Yeah, it's because we're mixing ethanol and water, we're mixing 25 milliliters plus 15 milliliters of water. So we need to add those together to get the total, and then we have to multiply by 100. So it's basically 25 over 40 times 100, right? And what's that?
62.5.
There you go. So that's a basic calculation of the percentage. Let's do a more complicated one, okay? So now that we've got the definition of what it means to have a certain, percent ethanol by volume, or in this case, we're going to use alcohol by volume. Let's imagine mixing two different solutions together in a beaker. So in this problem, we are in the chemistry lab, and we have a solution, which I'm going to call solution A. It's 25% alcohol by volume. We'll just say ABV for that. We'll say solution B is another one I have in my lab, and it's 75% ABV. So here's what we do. We start by taking 45 milliliters of solution A and pouring it into a beaker. So the question is, once we've done that, how many milliliters of solution B would I need to add to that beaker to create something that is 35% alcohol by volume? Okay, so let's just think about it conceptually, right? We have solution A, which is only 25%. Solution B is a much more potent solution, right? It has more alcohol by volume. So if we add to solution A, we should get a higher percentage. You can see that, right? But the question is, how much would I need to actually get that particular percentage? Okay? There's a question very similar to this on the homework you might have seen, involving mixing cement and sand, but this is pretty similar to that. Okay, so let's go through it. For this one, what I'm going to suggest is to start by drawing a picture, okay? So we're going to let X equal amount of solution B that I need. Okay? So what we're doing is we're taking solution A, which is 25% alcohol by volume. And how much of that do we start with?
45 milliliters.
So I'm just going to put that we have 45 milliliters of that. But then I'm going to add to that some unknown amount of solution B. So let me just say that as I'll have X milliliters of solution B that I'm adding to that, okay? So those are being mixed together. And then I'll just note that my solution B is 75% ABV. And then once I do that, I have a mixture. So if you see how I'm doing the picture, I want to specify here what the percentage ABV is. What is that for the final mixture? Just stated in the problem, right?
35.
Yeah, so we want this to be 35%. Okay. And on the bottom, I'm writing how much we have, right? So how much volume do I have in this final mix? Yeah, I'm gonna write this as 45 plus X. Just add the two volumes together of, let's just call it the new solution. All right, so that's a picture of what's going on. Now, immediately, that doesn't tell us what equation to write down, but I want you to notice something about this, okay? Like, before I actually mix these two together, right? There's some amount of alcohol in there, right? We don't know what it is, but there's some amount of alcohol, right? That's the same amount of alcohol that's here after I've mixed them together, right? There's no new alcohol appearing out of nowhere, and I'm not losing any. I'm just mixing two things together. So my point is, my amount of alcohol in milliliters here between these two equals the amount of alcohol here in the final mix. Does that make sense? I don't change the amount of alcohol I'm dealing with just because I mix two things together. So I'm just noticing that fact, and that's actually how we're going to come up with our equation, okay? Now, let's go back to the definition of percentage, percent alcohol by volume. That would be the volume of alcohol in a given mixture divided by the total volume. And then I'd multiply that by 100, right? Now we want to solve for the volume of alcohol in this formula. So just rearrange things a little bit. So if I take this 100 and I divide it, it goes on the bottom over here. And if I take this total volume and I multiply it on both sides, it comes to the top over here. So in other words, the volume of alcohol would be the percent ABV divided by 100 times the total volume. Does that make sense? I'm just taking the definition of the percentage and then rearranging it to say, let's solve for this volume, okay? And like I said, the way we're going to come up with our equation is to say the volume of alcohol over here is the same as the volume of alcohol over here. We're going to use this to write down what that is, okay? So we good on what the strategy is? Okay, so how about we start here with our original 45 milliliters of solution A. Solution A is 25% ABV. So the amount of alcohol contained there is 25, that's our percentage, divided by 100, and then multiplied by our total volume, which is 45 milliliters. Okay, and then I'm adding to that X milliliters of solution B. If I want to say how much alcohol is there, remember I'm taking the percentage, which is 75 in this case, divided by 100, and then the total amount of that solution B is what we don't know, it's X, okay? So what I've just done is I've written down a formula for the total amount of alcohol between these two beakers right here, okay? Then, on the other side of the equation, I'm going to say that equals the total amount of alcohol here, because that doesn't change. And I'm going to use the same exact strategy to do that. I'm going to take 35% divided by 100, and then our total volume for this final mixture is 45 milliliters plus X. Okay? So are we all good with how we got here? This, once we're here, the rest is pretty easy compared to getting to this point, right? So any questions about how we got here? The rest is just crunching the numbers. Okay, well, now that we're ready to crunch the numbers, this first number, 25 over 100 times 45, if you work it out, is 11.25 milliliters. That's what I'm getting. This next one is 75 over 100 times x, so that's 0.75 times x right there, okay? Lastly, I have 35 over 100 times 45, and if you crunch that, you get 15.75 milliliters. And then lastly, we want to distribute this into the parentheses and multiply it by this x. So I have 35 over 100 times x, or 0.35 times x. Okay, that's what we're dealing with. Okay, we're almost there. If I take 0.75 minus 0.35, then I can combine these two terms that have the x in them. You see that? So what do I get? 0.75 minus 0.35 is just 0.4. And then if I take 15.75 minus 11.25, I can combine these two terms. And that's just 4.5. Okay. So the last thing I do to solve for x is 4.5 milliliters divide 0.4000. And then what do I get? Can someone crunch that for me real quick? 11.3. So that's how much of the solution B I have to add to solution A, and then get a final mix that's 35% ABV. Right? So this one's a little trickier, right? But hopefully you see how this works. Okay, we good on this? So we'll keep moving. This next one, like I said, we want to tackle problem solving, basic word problems like the ones we've done just in the last 20 minutes or so. We also want to review some basic trigonometry because this is going to come into play a lot in this class. So this is a classic trig problem where you have a ladder that's propped against the wall. The ladder itself is 28 feet long, and the bottom of the ladder is 11 feet away from the base of the wall. So there are two questions I want to answer here. How high is the top of the ladder here off the ground? And what is the angle, shown here as theta, that the ladder makes with the wall? Okay, so to answer these questions, I'm just going to give you a hint. To get h, what's a fact about geometry you can use to solve for h? Can anyone think of it? Pythagorean theorem gives you h. What's going to give you theta? Any trig function you want, basically. Just use sine, cosine, or tangent. You can get it any way you want. Okay? So try it out, see what you get. Got the first part, that's good. we got for H? Nice. Okay, so again, I just want to make sure we cover everything I wanted to cover today, so I'm going to have us reconvene and just go through this real quickly. So basically what we have is a right triangle. I'm going to just copy down the right triangle that you see in the picture on the slide. The angle theta is up here. Now, where is my right angle on this picture? It's down right there, where the wall meets the ground, basically. And what is this long side over here? Yeah, so that's our hypotenuse, and we know the value of that, right? 28 feet. What would we call this side down here?
Opposite.
It's the opposite side because it's across from where the angle theta is. And what is the value of that? That's 11. And then what do we call this side? We call that the adjacent side. And that's our h, which we don't know. Okay, so how does the Pythagorean theorem go in this case? We squared this side, we squared this side, and that equals the hypotenuse squared. So let's just write it as opposite squared plus adjacent squared equals hypotenuse squared. For opposite, I'm plugging in 11 feet. For adjacent, that's my unknown h. For hypotenuse, that's 28.0 feet. So I'm trying to solve for h. So let's subtract 11 feet squared on both sides. H squared is equal to 28.0 feet squared minus 11.0 feet squared. Now I have h squared. What do I need to do to solve for h? I better square root both sides. And that gives me h equals that. You can plug that into your calculator. And what do you get? 25.7 feet. That is correct. Okay. Why don't we do a quick review of the trig functions? How about? Trig functions. Okay. What is the definition of sine of theta? That's the opposite side over the hypotenuse. What is the definition of cosine? Adjacent over hypotenuse, okay? And then what is the definition of tangent? Opposite over adjacent. This is super relevant to physics, all of this trig stuff. Now, I don't know, which one do you want to use? Just shout one out, I don't care. Sine? Okay, I heard sine, so let's do sine. Sine theta in this case is opposite, which is 11 feet, divided by hypotenuse, which is 28 feet. So what do I need to do to solve for theta at this point? It's the inverse sine, or arc sine. These mean the same thing, right? And I just have 11 over 28, basically, because, the units can cancel. And what do we get for this angle? 23.1, and that's in degrees, right? Okay, so are we all good on this example then? Any questions? All right. Okay, I'm going to skip this example. It's very similar to the one we just did because there's some other stuff I want to get to. Basically, you can use trig to look at the shadow that something is casting and then try to figure out how tall that object is. So we can tell by the length of the shadow of the tree how tall it is. Basically, we just make a little right triangle again. So the math is kind of the same. But again, I need to get to some other things today, just so we're prepared for next week. And that brings us to orders of magnitude, okay? Has anyone heard this term before? Are we familiar with this idea of order of magnitude? So if you're not, here's how it works. Basically, an order of magnitude is sort of an estimate, a very, very rough estimate, just to get a sense of what ballpark is a certain number in. We don't care exactly what the number is, we just want to know how big it is to the nearest power of 10. Okay? So as an example, if we have the number 2,500, and I only care about its order of magnitude, it's closest to 1,000. That's the nearest power of 10. It's closer to 1,000 than 10,000, right? So we'd say 10 to the 3. That would be our power of 10 that this is closest to. Now sometimes we compare two different numbers and we try to ask, are they of the same order of magnitude? And here's how you can tell. If you have two different numbers and you take the big one and divide by the small one, if what you get when you do that is between 1 and 10, we just say that they have the same order of magnitude. So, okay, let's just do a quick example, okay? Let's say we have 709 and 1,050. Can someone just punch into the calculator 1,050 divided by 709 real quick and tell me the result?
1.48.
Yeah, so 1 and then some change, right? So they're definitely the same order of magnitude, right? However, we have 402, if those are the numbers we're comparing, 400 divided by 2 is what? 200, which, those are 2 orders of magnitude different. I'm leaving a link here. I'm not going to go through this right now, but if you go to these lecture slides on Canvas, you can click this link. And what it shows you is basically a size scale for different things in the universe, going all the way down to the subatomic realm, all the way up to the size of clusters of galaxies. So you kind of zoom way out, see the biggest things in the universe, and zoom way in and see the smallest things. And at each step, it's telling you the order of magnitude in terms of size that you're looking at. So it's just a useful tool to get thinking about this idea. Okay, so related to this idea of order of magnitude is something called a Fermi problem. So Fermi problems are named after this guy. He's a physicist, an Italian physicist named Enrico Fermi. And he's basically famous for a lot of things, but one of them is coming up with these fun little puzzles, which basically involve making an order of magnitude approximation of something without having a lot of data to go off of, just sort of making guesses at what the number could be. There's one famous example of this, which is Fermi was able to estimate how many piano tuners, like people who work, their job is tuning pianos, in the city of Chicago. Again, he didn't look up any numbers, he just made some reasonable guesses, made a quick calculation, and got pretty close to the answer. So we're not going to do that one. That one's in the textbook if you want to see it. But the one we are going to do is this. How many ping pong balls can fit in this room? Again, we're not going to measure anything. We're not going to look up any numbers. We're just going to make some reasonable guesses, and we'll get pretty close. I guarantee you we'll get within an order of magnitude of it if we make the right guesses, okay? So you ready to do this one? How many ping pong balls can fit in this room? Before we actually try it out, I don't know, does anyone have a guess, just whatever comes to the top of your head? How many do you think it's going to be? Like 1 million? 1 billion? 5? Okay. Probably a little more than 5.
90,000?
Let's find out. Okay, so this room has a weird shape, okay? Let's ignore that. Let's pretend this room is just a box. If it's shaped like a box, that's a lot easier to deal with than whatever the hell this shape is, right? And what is the shape of a ping pong ball? It's a sphere. So basically, we're asking how many tiny little spheres can fit into this room, which we're going to treat as if it's a box. Okay? Because again, we don't care about the details. We just want to get a rough estimate. Okay. So I'm going to start by saying this. If the room is completely filled with ping pong balls, then the total volume of the room, the total space in this room is equal to the total volume of the ping pong balls. And let's say n ping pong balls. N is the number that we have, okay? And we're trying to figure out what n is equal to. Now, again, there's some details that would make this more complicated if we wanted a really precise calculation, like there's always an empty space between some of the ping pong balls. You can't perfectly pack them together so that every bit of volume of the room is used. We don't care about that. We're just trying to get a rough estimate, right? So, the way we can say this is the volume of the room, that's what's on the left side, right, is equal to n, that's how many ping pong balls there are, times the volume of one ping pong ball. That make sense? So that's what it means to fill the room up, okay? And what we're interested in is n. So the number of ping pong balls we can fit in here is just the ratio of the volume of this room divided by the volume of a ping pong ball, okay? Now at this point, we're going to put in some formulas. So again, I don't have a nice formula for the volume of this room because it has a weird shape. But if we pretend it's a box, it has a length, it has a width, and it has a height, what is the volume of a box that has a length, a width, and a height? Just multiply length, width, height, okay? That make sense? Does anyone remember the formula for the volume of a sphere?
Isn't it like 4/3 pi r squared?
Very, very close. 4/3 pi r cubed, actually. Yep. So we all understand what these variables mean. Length, width, height is for the room. R is for the radius of a ping pong ball. Okay? So now we have to just look around this room and come up with a reasonable guess. I want to use meters here, okay? We've got to get used to working in the SI system. So let's say, I don't know, what's the distance from that wall to that wall? Just guess. 10 meters? I think that's a good guess for length, okay? I'm going to put in 10 meters for that. Okay, what about, from this wall to that wall back there? So a meter is just over 3 feet, right? So 30 meters might be a bit much. That would be like 100 feet. What do we think?
Probably more.
Maybe 15 meters? Sound good? Okay. What about the height, just floor to ceiling? Could you jump and touch the ceiling? Maybe? I don't know. Maybe looks to me about the height of a basketball hoop, right? How high is that?
9.
It's like 3 meters? 3 meters is about 10 feet. That makes sense, right? Okay, and then I have 4/3 pi, and then I'm going to take the radius of a ping pong ball and put it in there for R. So I don't know, just try to imagine what that looks like holding it in your hand. It's definitely way smaller than a meter for the radius, right? What would the radius be closer to if it's just something you could, fit in your hand like that? Centimeter? Centimeter sounds good. Let's do that. Again, Just trying to get in the right ballpark, right? So a centimeter is 0.01 meters, isn't it? So I'm going to take that and cube it, because I need my units to be consistent so they can cancel out. Okay? Now what does this come out to? Can someone try it out? So 10 times 15 times 3 divided by 4/3 pi times 0.01 cubed on the bottom.
$170 million. That doesn't sound right.
Yeah, no, that's, and what would that be in scientific notation?
1.07 times 10 to the 8.
10 to the 8?
Yeah.
Seems like a lot, but there's a lot of space in this room. The size of this room compared to a ping pong ball is pretty substantial, right? And again, this is just a rough order of magnitude, but something like tens of millions, hundreds of millions of ping pong balls could reasonably fit in this room, okay? That's what we're finding here. So, do we have any questions on that? Okay, let's have you try one out, which is, in a lifetime, try to estimate how many gallons of water a human will drink to the nearest power of 10. So I'm going to give you some rough choices. Is it like 10 to the 2, which is like 100? Is it 10 to the 4, which is 10,000? Is it 10 to the 6? Is it 10 to the 8? Try to work this out on your own. And here's what you'll need to do, right? Just make some reasonable guesses about A, how much water, try this, how much water does a person drink in a day? You could probably estimate that a little bit better than in a lifetime. And how long does a person live? If you know those two things, you know the answer to this question. And again, it's going to vary depending on the person, but there's only one answer in this set of choices that makes any sense at all, okay? So try it out, see what you get. So you can start with this. How many gallons in a day would a typical person drink? One. Yeah. One-ish, right? We have. Yeah. Just multiply that by how many days a person lives in a lifetime, you should have your answer. Okay. All right, so I see a lot of people have this, so we'll go through it together. What's the answer, by the way? Yeah, B has to be that. There's no way you could survive in a lifetime with just 100 gallons of water. All of the last two choices are way too much. It's B, and I'll go through it with you guys to see why. So Here, let's start off with some estimates. What's a reasonable amount of water to drink in a day?
1 gallon.
A gallon? I mean, a gallon, yeah, that's kind of a lot, but let's maybe say half a gallon, okay? Doesn't really make a difference, but half a gallon, how about? What's the typical lifespan? Like, how long does the average person live?
85.
80, yeah, 80 sounds good to me. Again, we're just trying to get in the right ballpark here. So here, what I'm gonna do is treat this one as kind of like a unit conversion. I should say half a gallon per day is what I meant to say there, right? But I'm gonna treat this like a unit conversion where we start with the quantity 80 years, and then we wanna translate that into gallons of water. So how about we do this? Let's translate 80 years into a number of days. What's the conversion factor I would use to go from years into days?
365 over 1.
365 days on top, 1 year on the bottom, and then cancel that out, right? Then the next conversion factor is what I estimated over here, which is how many gallons of water per day. So I'm gonna have half a gallon of water on top, 1 day on the bottom, and then cancel that as well. That's how I'm thinking about this as a unit conversion. So just do this, do 80 times 365 times a half, and what does that work out to? Yeah, it's 14,600 gallons, but we don't care so much about the extra digits here. Let's just say to the nearest power of 10, it's about 10,000, which is about 10 to the 4 gallons, okay? You all good on this? Okay, so I hope it's clear that this is the only reasonable answer. Anything else wouldn't really make any sense. Okay. Again, I think I'm going to skip over this one. This is another Fermi problem where we make an estimate of something. This one is kind of interesting. I'll just tell you what it is. If we have time, we might get back to it next week. But it says, if all the people in the world were standing like in a huge crowd, just packed in shoulder to shoulder, how much land area would we all take up? Okay, so you can see how you might be able to estimate this sort of thing in the same kind of way, right? But we'll skip over this one because what I want to get to in the last few minutes here is something called dimensional analysis. And this is a really important tool in physics to analyze equations or analyze certain results that you might get when you're solving a problem to check to see if they make sense. So when we talk about dimensions, in the term dimensional analysis, the dimensions of a quantity just refers to the type of quantity that you're dealing with, but we're not giving any specific units. Okay, so it's just what type of quantity is it without referencing any kind of unit. So let me give you an example. Length, that's a dimension, time, and mass. So for length, let's say, I could use a specific unit like meters or inches, but if I just say length, I'm not making reference to those units, right? Same with time. I could measure that in different units, but I just care, in this case, that something has dimensions of time, okay? So if we give an example here, let's take speed. Speed is defined as distance traveled divided by how long it takes you to travel that distance. In other words, it's a length, that's how far you traveled, divided by a time. So that's how we would refer to the dimensions of this thing called speed. It's a length divided by a time. And then again, you can plug in your favorite units. You can say meters per second, miles per hour, kilometers per second, whatever you want, but those would be the dimensions, okay? Here's another example, density. We all familiar with the idea of density? This is mass of something divided by its volume. So mass, well, that's dimensions of mass. That's pretty straightforward. Dimensions of volume, what would that be? So volume is not the same as a length, right? It's not the same as an area. To calculate a volume, we have length cubed, basically, right? Meters cubed, centimeters cubed. Those are volumes. So mass divided by length cubed is how we would refer to a density, okay? And again, pick your favorite units. In SI, it's kilograms for mass, meters for length. So we'd say kilograms per cubic meter. Okay, so those are just some examples of what we mean by dimensions. Now, not every quantity has dimensions. There are things called dimensionless quantities. And those are just pure numbers that don't have any units attached to them. It doesn't even make sense to attach a unit to them. So, for example, let's say we have two distances or two heights. Let's say my height divided by your height. That's just a ratio. The units cancel out when you take one height divided by another. So you're left with a dimensionless quantity there. Or if I'm just counting things, like if I just counted the number of people in this room, that's a dimensionless quantity too. It doesn't have any units attached to it. Make sense? Okay. So there are two rules when it comes to dimensional analysis that every single equation you encounter in physics has to follow. And here are the two rules. Anytime you see an equation that relates any type of physical quantities you want, the right-hand side and the left-hand side of the equation have to have the same dimensions. So for example, if I set a length equal to a time, that would just be a nonsensical equation. That there's no way that equation could even be correct because it's not consistent dimensionally. The left-hand side, the right-hand side of any equation have to have the same dimensions. Also, whenever we add or subtract quantities, they have to have the same dimensions too. I can't add a time to a length. That doesn't make any sense. I can only add together or subtract like quantities. They have to have the same dimensions. Actually, related to this, is it possible to divide quantities with different dimensions? We said we can't add or subtract quantities that don't have the same dimension, but can we divide or multiply? Yeah, there's no problem with that. Meters per second, right? I could take a length divided by a time. That gives me a speed. But we can't add or subtract them. Okay, so these are the two rules. They're pretty simple. And we know that if your equation doesn't obey these rules, it can't be correct. You don't even have to look into it any further. If it doesn't obey these rules, you just know it's wrong right off the bat. So this is very useful when you're doing any kind of work using physics equations. You might be doing like a whole page of algebra to get to some result. You might want to know if you did the right work, right? It would be a shame if you did all that work and the answer was wrong and you just didn't see it. So one way you can verify your work is to just check that any equation you write down follows these two rules. It's a really simple check you can do, and if it doesn't pass the test, then you know there's been a mistake somewhere, okay? So we're going to do two examples of this and probably wrap up after that. I have two equations that you see here. In the first one, I have v equals x over t plus x squared times t squared. Let's just be clear on what we're talking about. X is a distance, t is a time, and v is a speed. So does this pass the test? We'll work that one out. And then as our second example, x is a distance, t is a time, v is a speed just like before. And then there's this constant c that we're putting into the equation. So the second question is, what would this constant c have to be? What would its dimensions have to be, in other words, for this equation to make any sense? Okay? So we'll work out these two examples and then we'll wrap it up here. So are we all clear on what the examples are? So let's go through it. Okay. So I'm going to start with the first equation, which says v equals x over t plus x squared t squared. Now I'm just going to show you some notation, okay? I'm going to put a little bracket around each one of these terms. when I do that, that just means give me the dimensions of that thing, okay? So v is a speed, right? It's a length divided by a time. What x is a distance? It has dimensions of length, okay? So I'm going to write capital L for anything that has dimensions of length, capital T for anything that has dimensions of time. And then in my last term, I have x squared times t squared, right? So that's a length squared times a time squared. So right away, can we see, does this work? Is there something wrong with this?
They're adding.
So you can't add quantities with different dimensions. So this is incorrect. Okay, we don't even need to know anything about this equation other than its dimensions, and we can automatically say it's incorrect, okay? Now, that was the first example. The second example from the slide says, let's modify that equation slightly. And let's say v equals x divided by t plus c, some constant, times x squared t squared. So now it might be correct that we've added this new term c here, but it has to have the right dimensions for this all to work out, okay? So we'll do the same thing we did before. I'm going to say dimensions of this, dimensions of that. I just, when I put the things in brackets, we're just saying, show me what the dimensions are. So, just like before, speed is length over time, right? And on this side, we have length over time as well, for x over t. That's a length over a time. Then, I don't know what the dimensions of this thing c actually are, so I'm going to leave that as an unknown. You see how I'm notating this? And then I have x squared, which is a length squared, and I have t squared, which is a time squared. So if I take a look at that last term, do we agree its dimensions have to be length over time for this to work out? Because I need to, if I'm going to add a length over time to something, it better be another length over time, okay? See what I'm saying? So this whole thing better have dimensions of length over time, so the dimensions of c times length squared times squared equals length over time. So the dimensions of that constant c better be, just divide out L squared and divide out t squared. We're going to get 1 divided by L, and then if I put the t squared on the bottom along with this t, it's t cubed. So whatever this thing c is, it better have dimensions of 1 divided by length times t cubed. Okay, that's the idea here. Oh, I'm sorry, can't see that? Yeah. Okay, so we're going to end the lecture here. Next week, we'll start up on chapter 2. And if you're in the Thursday lab, we're going to head over to the lab room right now and do the first experiment.